Welcome back. We are in lecture 7B of BJT amplifiers. We will discuss here about the common emitter amplifier. In the previous lecture, we have introduced about the BJT amplifiers and its significance. Let us discuss on the common emitter amplifier, which is the first classification. Then we will discuss on common base and common collector. So the common emitter amplifier we are taking in the form of voltage divider biasing. Now what is voltage divider biasing? So here we have the resistor R1 and resistor R2 which is connected on the base side. So these act as voltage divider. If we see the circuit, there are capacitors C1 and C3 which are known as coupling capacitor, and they are connected on the input side and the output side. So here the C1 is the capacitor which is connected on the input side, and the capacitor C3 which is connected on the output side of the BJT. There is one capacitor C2 which is known as the bypass capacitor, which is connected between emitter to ground. So the capacitor C2 which is connected between the emitter point and the ground, this is known as bypass capacitor. The signal which we apply at the input to the base terminal using the capacitive action is the input voltage what we can apply, and this is the AC signal. On the other hand, the output signal we can measure taken capacitively from the collector to the load. So here we have the output voltage which we will be measuring at the collector circuit, and there is a load resistor RL which is connected at the output. Emitter is common to both the input and the output signal. So if you see the emitter junction, here it is common between the input side and the output side, hence it is known as common emitter amplifier. When we talk about the bypass capacitor C2 in the circuit which is in parallel with the emitter resistor RE, this will be short the emitter to ground at the signal frequency, ensuring no signal flows at the emitter. So it has some special significance in the common emitter circuit. These amplifiers operate in both the AC and DC modes, but the common emitter designation especially refers to the AC operation. So we are not going to consider the DC mode in common emitter. We are going to consider only the AC operation mode. The output signal that we get is 180 degree out of phase with respect to the input signal. So there is a phase inversion. So whatever the input we are giving, the AC signal, the output we will be getting at 180 degree out of phase. Now how phase inversion occur? In order to understand that, let us take that if there is a change in the input voltage, then there will be change in the base current. This will change the collector current, and there will be deviation of the BJT operation from the Q point. So about the quiescent point we have discussed very detailed in the previous lectures. Now if the base current increase, then the collector current will also increase, and the voltage drop across the collector resistor RC will also increase. This leads to decrease in the voltage at the collector. So due to the collector current which is increased, now this will result in decrease at the voltage at the collector because you will have certain drop. Thus a change in the input voltage cause the opposite change in the collector voltage, which result in the phase inversion of the transistor. So what is the conclusion? That the common emitter amplifier provides the voltage amplification. So you will be getting a voltage which is more at the output than the input, but the output will have 180 degree phase inversion. Let us understand this with an example of a DC equivalent circuit of common emitter amplifier. Now to determine the DC bias values of the voltage, AC components need to be removed, such as the coupling capacitor and the bypass capacitor, since they appear open for the DC. So you need not to consider the coupling capacitor or the bypass capacitor because we are considering the DC effect and those will be open. We also need to eliminate the load register as well as the signal source, that is not needed because we are doing the DC analysis. Now the Thevenin resistance, if we want to compute, then that is the resistance which is parallel to R1 and R2. So these two resistor parallel combination, which is the equivalent R1 R2 divided by R1 plus R2, will give you the Thevenin resistance. So the demo values whatever we have taken, from this we can get the R Thevenin as 5.1 kilo ohm depending upon the register value of 22 kilo ohm in R1 and 6.8 kilo ohm in R2. Similarly, the Thevenin voltage, if you want to calculate, so that depends upon what is the source voltage you have, that is the VCC, and this is the net voltage which appears across the R2. So the parallel combination that we get between R1 and R2, if we are calculating at R1, then on the numerator we will have R2. This is in accordance with the voltage division rule. So the source voltage which we have here is 12 volt. This gives the Thevenin voltage as 2.83 volt. Similarly, the emitter current we can calculate. So this derivation we have done in the previous lecture, how to obtain the emitter current in the common emitter configuration. So the formula we can use directly and we can get the emitter current, where beta is basically the gain at the DC. So here the example they have considered the beta to be 150. Collector current and emitter current are approximately equal, so which is equal to 3.58 milliampere, and the emitter voltage we can calculate from the Ohm's law as IE/RE product. So that gives to be 2 volt. Now once we have calculated these values, the other values of base voltage, collector voltage and collector to emitter voltage we can easily obtain by applying proper KVL equation in the circuit. So that will give us the base voltage, collector voltage and collector to emitter voltage. Now AC signal operation when we are doing at the amplifier, then the capacitor will be treated as short. Now these capacitors are basically C1, C2 and C3 which are connected in the circuit for the common emitter. They will be replaced by sorting the values, and the values make the capacitive reactance, because we know that Xc is equal to 1 by omega c in terms of the value. So what happened, this become negligible at the signal frequency. So when we talk about the signal frequency, this may be a 50 hertz. So here omega what we have is basically 2 pi f. So if we take the frequency to be 50 hertz, then the Xc value is very less, and hence we can neglect it. When we talk about the DC source, the DC source is replaced by the ground potential in AC analysis. The reason is it has negligible internal resistance and does not produce any AC voltage acting as AC short. So we can take directly as 0 volt in the DC source. The AC equivalent circuit, if we see, then both the RC value and R1 are connected to the AC ground, which is linked to the voltage of the collector in the actual circuit. The bypass capacitor C2, which keeps the emitter at AC ground, make it the circuit common point. So here we can see R1 and R2 are in parallel, and you have the resistor RC, which is the collector resistance, and this is without any input signal. So that is the AC equivalent circuit of common emitter amplifier. Now if you apply the AC voltage at the base, so you have the voltage Vs with internal resistance Rs which is connected at the base. Now this AC source is connected to the base. So this is the base terminal, which is the input we are giving to the base terminal. The base voltage depend on various resistances. So we have various resistances which are present in the circuit that will govern the base voltage. So the factors that is affecting the signal voltage, so if the source internal resistance, that is Rs, this is 0 ohm, the entire source voltage will be appearing at the base. So all the voltage we will get at the base circuit, because the voltage at the base will be appearing at R1 and R2 as well as the base. These all will come in parallel and there will be no drop across Rs. With non-zero internal resistance, means some value is there for Rs, 3 resistances must be considered. So we have to consider the resistance of the source, we have to consider the bias resistance, which is the parallel combination of R1 and R2, and also the AC input resistance at the base. So the total input resistance which we can get from the parallel combination of R1, R2 and the input resistance of the base, this is the parallel combination of these resistors. And we can see here in the circuit R1, R2 and register of the base, these are in parallel combination. So these would give us the total internal resistance of the base. Now if you want to obtain the voltage divider effect, which is because of the source voltage, this is divided between the resistance of the source, that is Rs, and the total internal resistance that we have calculated now. So the voltage we can easily get in terms of voltage division rule formula. What is the voltage that is appearing at the base? So resistance plays a very important role in calculating this voltage. If we take some special cases where the source resistance is very less than the internal resistance which we have calculated, then we will be getting that the base voltage is approximately equal to the source voltage. So this is what it is written here, that this means that voltage at the base is nearly equal to the input voltage if the source resistance is much smaller than the total input resistance. So there is some design trade-off we can do. High input resistance is desired to minimize the signal loading. So whenever we want to minimize the signal loading, we prefer high input resistance. Small resistance are necessary for stable biasing. So if you need stable biasing, we go for the small resistance. Achieving both high input resistance and stable biasing involves trade-off between the component selection. So this resistor has to be appropriately chosen to have this signal loading and stable biasing into our consideration. If we calculate the input resistance at the base, then we use the simplified R parameter model of the transistor, which we have discussed in the previous lecture. What is R parameter and H parameter, and that is used to derive the AC input resistance at the base. So this is what we have, the R parameter transistor equivalent model, where we have the resistor RE dash. This resistor is at the emitter AC resistance, and we have a dependent source here, which is the current source. Now the input resistance of the base is basically the voltage of the input by the current input, which is the base voltage by the base current. Base voltage is again equal to IE into RE dash. So we can easily obtain this voltage VB, which is in parallel with the emitter resistor, and the emitter current is approximately equal to the collector current, where the base current is approximately equal to emitter current by the current gain, which is beta. So the input base resistance, if you want to calculate, that will come to be the base voltage by base current. Now here we can take out the IE component, and what we got is the current gain beta multiplied with the resistor of the emitter. When we calculate the output resistance of a common emitter amplifier, the output resistance will be approximately equal to the collector resistance. But for a more detailed expression, we can take the parallel effect of the collector RC dash also, which is the internal AC collector resistance of the transistor, to calculate the R out. Since the collector RC dash resistance is very greater than RC, the approximation is usually varied. So this value we can take as the approximation. Now the voltage gain, if we want to calculate the voltage gain, again the meaning is output voltage by input voltage. So that is coming to be the collector voltage by base voltage. So we have to obtain the collector voltage and the base voltage. In terms of the formula, if we see, the collector voltage is nothing but alpha, which is again the current gain, multiplied with IERC, and this is approximately equal to IERC only because alpha value is less, and the base current will be IERE dash. And if we divide these two values of collector voltage and the base voltage, we get the voltage gain as IERC, that is the resistor of the collector here, and the current of the emitter divided by whatever the resistance you have at the emitter multiplied with the emitter current. These equations represent the voltage gain from base to collector. Now here you can see this is the base what you have, and here you have the collector. So what is the voltage gain from base to collector? If it is asked in the problem, we can directly use this expression. overall amplifier gain from the source voltage to the collector, we must include the attenuation effect also in the input circuit. Now, what is attenuation? It is basically the reduction in the signal voltage as it passes through a circuit corresponding to a gain of less than 1. So, when we need to calculate the voltage gain from base to collector, we will be using this expression, but overall amplifier gain from source voltage to collector, if you want to obtain, then we need to take the attenuation into account. So let us understand what is attenuation with an example. If we have the signal amplitude which is reduced by half, now it is less than 1, so attenuation is equal to 2. Now the gain what we have is inverse of the attenuation, so that is equal to 0.5. Let us take one case study. If the input signal is 10 millivolt and output we have 2 millivolt, then we can say the attenuation is input 10 millivolt by the output 2 millivolt, so that is equal to 5. Then the gain will be inverse of the attenuation, which is equal to 0.2. So what are the key takeaways that we have from this discussion is attenuation reduces the signal voltage as it passes through a circuit. Attenuation and gain are always inversely related to each other, and the overall gain of the amplifier will depend upon both the voltage gain and the attenuation of the input circuit. So here we have the complete circuit that describe the attenuation effect, the voltage gain base to collector, and then we get the overall voltage gain from the source to the collector. So attenuation, if you want to calculate, that is equal to the source voltage by the base voltage. This will be coming from the total input resistance and the source resistance. Whereas if you want to calculate the total overall voltage gain, then we have to multiply these two gain, which is due to the attenuation and also due to voltage gain to the collector, then that is coming to be the collector voltage by source voltage. So depending upon the problem, we have to determine this voltage gain appropriately. There is certain effect of emitter bypass capacitor on the voltage gain. So the C2 capacitor will short the AC signal around the emitter resistance, and this will maintain the emitter at the AC ground. Then the maximum gain that can be achieved is basically RC by RE dash, and we can say that the capacitive reactance XC must be very small compared to the emitter resistance across the operating frequency, and a rule of thumb we take that emitter resistance should be greater than 10 times the capacitive reactance at a minimum operating frequency. Now we ensure that the capacitive reactance is approximately at 0 ohms for optimal performance. So if you do not have the bypass capacitor in the circuit, then the emitter isn't at AC ground and the emitter resistor appears in the AC path, which will increase and reduce the AC voltage gain. So this is the voltage gain what you have for the circuit. So here, if the emitter resistor is not there in the circuit, then the voltage gain will be reduced. So we will see what is the effect of load on the voltage gain. So we have a load here which is connected in the circuit, and this is the complete amplified circuit of common emitter in the voltage divider bias, and we will take the AC equivalent. So we can remove the capacitor C1, the capacitor C2 and the capacitor C3 with 0 values because this will be open. Then these two resistors R1 and R2 will come in parallel, and you will be also having resistor RC where RC will come in parallel with the resistor RL. So the total AC collector resistance, if we see, this will be parallel combination of RL and RC because C3 will not be there. And if we replace RC with small rc, then we will get the voltage gain what you have is RC by RE dash. If the small RC value is very less than RC because of the load resistor, the voltage gain will be decreased. But if the load resistor is more than RC value, then both the resistance RC and capital RC will be approximately equal. In that case, very little effect of the load will be there. So it depends upon which resistor values we are choosing in the network. So we need to know the stability in amplifiers. So stability is basically the measure how well an amplifier maintained its design values over change in temperature, or the transistor parameters, example beta. So if there is a change in the transistor parameter or the temperature, then the amplifier will operate at different values and then will not be any stability. So stability has to be there. The voltage gain will depend upon Re dash, which is sensitive to temperature, and IE. So this Re dash plays a very important role because they are very sensitive. And the current gain, whatever we get, voltage gain AV, is RC by Re dash. So Re dash changes, then the gain becomes unstable. Now, if there is no bypass capacitor, then AV, the voltage gain, will be having RC by Re dash plus Re. So for the stable but lower gain, if you want to reach, then Re should be very greater than Re dash. Now this value is more, so the voltage gain, we can say that it is RC by Re alone. So that will give stable, but the gain will be lower. So there is something which is known as swamping technique in the amplifiers. This is a compromise between the fully bypassed and unbypassed the register of the emitter. So this reduces the effect of Re dash on the voltage gain. So the register Re is split into two registers, Re1, which is unbypassed register, and Re2, which is the bypass register in the circuit. So Re1 and Re2 both will affect the DC biasing, but only Re1 will affect the AC gain. So the voltage gain, whatever we get now, is basically RC by Re dash plus Re1 alone. So this is equal to Re1. So if Re1 is very greater than Re dash, then we get RC by Re1 as the voltage gain. So it achieves a reasonable gain while maintaining the stability of the circuit. So swamping technique, again we connect two registers Re1 and Re2, splitting the registers of the emitter. This will achieve a reasonable gain. Swamping increase the input resistance. So whatever the input resistance we calculate at the base, this will be increased because of this Re1. So you have beta AC into the sum of Re dash plus Re1. Now if you want to obtain the current gain or the power gain for the this configuration, we can easily obtain from its circuit. So to obtain the current gain, we need to obtain what is base to collector current gain, which is equal to collector current by base current, and overall current gain is collector current by source current. So from this circuit, if we see, the source current we get is equal to Vs by the total resistance of the source plus the input resistance, and the power gain is nothing but the product of the current power gain, voltage gain, and the current gain. So we have already obtained this total voltage gain of the amplifier and the current gain, whatever we have here, IC by IS. If you multiply, then we will get the power gain. So this is power gain is product of voltage gain and current gain, because AV dash is basically VC by Vs. So this complete our discussion on common emitter amplifier circuit. We will be discussing the common base and common collector in the coming lectures 7C, 7D and so on. Thank you for now. See you in the next lecture.